SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture number 20 on force control. In the previous lecture, we looked at control of nonlinear systems and then stability. So we looked at the effect of dynamics on a system and how dynamics acts as a disturbance and how the controller for a robot system is actually a two-input system. And we'll move on further today to force control. Now, in whatever discussion we have had in the last few classes on control systems, that makes the assumption that the robot is not in contact with anything. That means the end effector is free to move in space and it is not contacting the environment in any way. Today we'll move on to force control. Now, force control is a case where the robot end effector is actually making contact with an environment for performing a task or for moving in a particular direction. Now, there are many applications where this is required. For example, in grinding, where the robot is using a grinding wheel and is grinding a particular surface. Okay, or you can imagine a case of writing. A robot is taking a pen and writing on the board. Okay, or a case where a robot is mopping the table. So the robot is taking a cloth or a sponge and is mopping the table. Now, in such cases, there is contact between the environment. And the most practical case where robots are extensively used is in electronic assembly. So in assembly, there is contact. So the robot is going to take a part and insert it into a hole, like in electronic assembly, and there is contact between the part and the hole. Okay, so today we'll look at cases where there is contact and how do we deal with such cases. So today's lecture is on force control, and let us see when there is contact between the environment and the robot end effector, how do we control such systems. Now we have to understand this concept of force control very clearly because the force space and the position space are orthogonal to each other. So as we go along, it will become clear that what do we mean by this orthogonality of force space and position space. So whatever we have discussed so far is in position control. We can talk of PD control, PID control, and simple other kind of controllers. But the basic assumption being made is that this is in free space. So the robot end effector, if I draw it here like this is my end effector, and the end effector is free to move, having some trajectory in space. Okay, there is no contact with an environment. Now in contact tasks, the robot has to apply a force and also move in a particular direction. What do I mean by that? For example, look at this example. So we have a wall and there is a grinding wheel. The robot is holding this grinding wheel. Okay, so this is the robot end effector and this is my robot manipulator. Okay. Now this grinding wheel is rotating, and how do we do grinding? The grinding wheel must apply a force in this direction. Okay, so this is a grinding wheel. So let me draw it a little bit larger like this. So this grinding wheel must apply a force on the environment. So it is touching this here. Okay, so this is rotating. So there is contact there. And when you are grinding, the grinding wheel must apply a force in that direction. And when it is applying a force, it should also move in this direction. Okay, so it is having some velocity extort in that direction. So now we see this is an application where a robot is holding a grinding wheel and it's applying a force on the wall where it is grinding and is also moving in a particular direction. Now, if you look very carefully, the force is in this direction and the velocity is orthogonal to that. Okay, so this is something I will explain more clearly as we go along, but please take note of this. Let's take the example of wiping a table. For example, this is a table. Okay, and let's say this is a table and there is some liquid which is spilled there, and the robot is using a mop. Say, for example, there is some cloth. Okay, and the robot is holding this cloth. Okay, using its gripper, and the robot is supposed to wipe this table. Okay, so this is another robot, right? Now the robot has to wipe this table. How are you going to wipe the table? There has to be a force in this direction, okay, to make contact with the surface of the table, and the end effector has to move in this direction, which is orthogonal to that force direction. Okay, that is how we do wiping. Now if you think how a human does wiping, exactly in the same way, we apply a force downward and then we move sideways. Okay, now what about writing? Now writing has exactly the same application, where when you're writing, for example, this is a piece of paper and you're writing, and this is for example your pen or pencil. Okay, so the robot end effector is holding this pen or pencil. This is the robot end effector, and this is my manipulator. So it is applying a force in this direction, and it is moving in that direction. That's how we write. Okay, so these are examples where a force is being applied, and there is motion in a particular direction. Okay, and these are applications that come under what we mean by force control. Now we also need to listen. We need to understand this concept of stiffness, which is very, very important when a robot interacts with the environment. Now, what this basically means is that you can have a hard environment, for example, a very solid wall. Now, you know that if you hit against the hard environment, what will happen? The wall will be damaged, or the robot end effector will be damaged. Okay, so there is a direction in which you can move very fast, or there is a direction in which you need stiffness to be very high, and a direction in which you need stiffness to be very low. Now stiffness can be looked upon as a spring. So let me so stiffness is something which we can represent like a spring. Okay, stiffness of a spring, which you are familiar with. So force is equal to K into, let's say, del X is the deflection here. Okay, so this K is sometimes called the stiffness of the spring. Now you know that if the stiffness is low, it means the spring is a weak spring. So what would happen is you can have a lot of deflection in there. F is equal to K into del X. Whereas if the stiffness is very high, then you can have very low deflection, okay, for the same force. So what it basically means is that your deflection del X here is equal to F by K here. So for a very high K, you'll have very small del X for the same F. Okay. So by changing this K in different directions, we can make the robot behave having high stiffness or having low stiffness. Now this is required. Why? For example, if you're moving in this direction, okay, and you're expecting contact to be made, then you must have very soft motion control. Okay. Whereas if you are having free motion, then you can have very stiff motion control. Again, it's a question of high stiffness or low stiffness. So if I have low stiffness against this wall, it basically means that the robot will not get damaged when it is going to hit the wall or make contact with the wall. Whereas in the free space, I can have a high stiffness, and because it is free motion, it is not hitting anything. Okay. So this concept of stiffness when a robot is making contact with a hard environment or is in free space is very, very important. Now it is, if you think a little bit, in the human hands also we have a lot of tissue on our fingertips, which gives us some amount of spring-like behavior. So when you hit a hard object, what happens is that impact force will be absorbed by the soft tissue, and our hands are not damaged. Okay, so let's look a little bit into the physical meaning of stiffness here. Now suppose you have this is the physical meaning of stiffness, that you have let's say a mechanical linkage like this, and the person is going to hold it and is going to push it. Okay, now depending on, and this mechanical linkage here, if you can imagine that there is a spring which is connected onto the joint, just for let's imagine. Okay, so if you push it, how it is going to behave would depend on the stiffness of the spring. Now for example, the person is pushing it here, and you can see it's very hard, difficult to move. It's behaving like a hard spring. Now this is behaving like a very low spring, low stiffness spring. Now again, the person is trying to push, it doesn't move. Now you see the person is trying to push, and it moves easily. Impact force, high virtual spring rates. Okay, low virtual spring rates. So basically what you're seeing is that this device or this mechanism is behaving like a spring, and whether it's a high stiffness or a low stiffness, that is the one that is going to determine how the system is going to behave. Okay, so here we saw that this was a low spring rate. Okay, so this is a very low spring rate. Okay, this is a high spring rate, the person cannot move. Okay, which is very easy to understand. Then we have this is followed by a low spring rate, so the person can move very easily. Okay, now what about a spring rate? The rate at which you are moving, now this is a very high virtual spring rate, so it's behaving like a very strong spring, so it's very difficult to move. Then it is behaving like a very soft spring, and it is very easy to move. That means your rate at which you can move is very high. Impact force. Okay. Now this basically gives you an understanding of this physical meaning of spring constant. Okay, that spring constant K, that by changing that, how you can make the system behave in a particular way. Now let's come to robotics, and now in robotics we can see that the robot arm can be made to behave in a particular way by changing its stiffness. For example, here is a case of a robot having a high spring. Okay, so if the person pushes it and leaves it, what will happen is the person has a high, the spring is very high. So what will happen, it will just come back quickly. So you see here, sorry, let us look at this. Okay, so the person is pushing it and leaving it, and it's just coming back. It's a very high spring. Okay, now this is not a way the robot hand should be behaving. Why? Because the person can get injured, okay, or the robot hand can get damaged. Now what about here? Now let's see a little bit more. So this is the next case where you're having a low spring, okay, low stiffness I mean. So in the case of a low stiffness, what would happen is, just see here very carefully, the person is pushing it, it has a low stiffness, so it is very easy to move it, and it can go and stay there. Now simply by changing the stiffness, sorry, let's look at a low spring rate first. This is a low spring rate. Okay, so you take it there, it goes back, and it comes down slowly. Okay, so by changing the spring rate, you can actually play with the way the system is going to behave by changing the spring constant. Okay, now this gives us an idea of, so look at this again. It is simply by changing that spring rate and by using different kind of controllers, which we call either stiffness controllers or impedance controllers. That is something what we'll be looking at today. Okay, this is giving you an idea in terms of robotics, how we can make the arm behave in a particular way simply by changing the stiffness. And I also hope you understand what we mean by the word stiffness here, physically. Now, the framework for controlling partially constrained environments, it basically means partially constrained means in some directions you can move and in some directions you cannot move. This is the meaning of the word partially constrained environments. Now let's try to understand this concept of position control. Okay, position control, and we have force control on the other side. Okay, so these are two things we are looking at today. Position control we have already looked at, PD, PID control in free space. What about force control? Now suppose we have an environment here. This is a wall. Okay, so we have a wall here, and you're applying, if you can imagine, you have let's say a pen or a stick in your hand, and you're applying a force in this direction. Okay, now you're applying a force, let's say 10 newtons in that direction. Can you apply a force on the wall? Yes. Why? Because the wall is giving you an opposite and equal reaction in this direction. Okay, that is the reason why you're able to apply a force. Now in free air, let's look at this question. Can you apply 10 newtons in air? Okay, so suppose at this point, let's say is air, and I'm going to apply 10 newtons. Can you apply in 10 newtons in air at some point? No, you cannot. Why? Because there is no opposite and equal reaction. This is not there, which means you cannot apply force. Okay. Whereas in this particular case here, because there was a wall, you could apply a force because there is an equal and opposite reaction. Okay, so you can apply a force only if there is an opposite and equal reaction, not otherwise. So that's the first point to remember. Okay, so this is point number 1, if there is an opposite and equal reaction, okay, coming from the surface. Now what about position? Now suppose I say you move in this direction with a velocity of 10 meters per second. Can you move in this direction, I mean on the surface of the wall? Move in that direction towards the right with 10 meters per second. Can you move? No, you cannot move. Why? Because the wall is constraining you. You can't move in that direction. Okay, but suppose I say you move in this direction with 10 meters per second velocity. Okay, so x dot is 10 meters per second. Now can you move? Yes, you can move. Why? Because there is no wall, nothing is obstructing you. Okay. So this essentially shows that you can have force control, you can apply force, or you can have position, but not both in the same direction. Okay, so please note this, position force cannot be applied in the same direction. Applied in same, so control of force and position in the same direction is not possible. Okay, so please note this. So force and position control cannot be done in the same direction. Cannot be done in same direction. Okay, So this is something very, very important to note, that if you can apply 10 newtons on the wall, you cannot move with 10 meters per second in the same direction. Why? Because the wall will not allow you. But position and force cannot be done in the same direction, but they can be done in orthogonal directions. Okay, so here you're seeing that we can apply 10 newtons towards the right, and you can have a velocity of 10 meter per second towards the bottom side or the top side. Okay, and you can see the force vector and the position vector are orthogonal to each other. Okay, so this is very, very important. Please remember the position force vectors are orthogonal if you need to control both of them together. So if you are trying to control position and force together, then how can we do that? That is a question that we are trying to look at in this application, okay, in this lecture today. So let's look at a particular few applications. Now this is a case of a crank being rotated. Okay, so a crank is a lever which is being rotated. Say for example, I want to rotate this crank so that I get a particular velocity, angular velocity like that. So how am I going to do that? I'm going to hold the robot is going to hold the handle. So this is my handle. The robot will hold the handle and is going to rotate the crank in a particular direction to get a particular resultant velocity. Now if you look at this task, in this task we are controlling what? Okay, so let's look at here in terms of control. What is it that we are controlling to do the task? What is the task in the first place? So the task is to rotate crank. This is my task. How am I going to do this task? The robot is going to hold this handle and is going to rotate in a particular direction. Okay. Now in order to do that, what are the various variables that we need to control? Okay. What are the various velocities and forces that we need to control? Now the first thing that we do is to fix a constraint frame. Okay. So a constraint frame is first fixed here. Now my this C, XC, YC, XC, YC and ZC is the frame which is fitted onto that. So my force and positions are going to be applied with respect to this frame now. Okay. Now if you look at this frame, we can divide the forces and motions into natural constraints and artificial constraints. So these constraints, okay, we saw in the previous case here when we talked about a wall, when we are able to apply a force or we are not able to apply a position control in a particular direction, this wall is behaving like a constraint. Okay, so it is constraining your task now. So similarly here, these constraints are divided into artificial constraints or natural constraints and artificial constraints. So these are natural constraints and there are artificial constraints. What is the meaning of them? Now the natural constraints are there because of the task itself. That means because of the nature of the task, these constraints are there. You can't do anything about it. Artificial constraints are the ones that you have to control, okay, in order to perform these tasks. Now, so how many of these are there, or what are the control variables? So we need to control what? We need to control, number one is the forces. Okay. Now forces would mean what? Forces and moments. Okay. So we have force and moment which needs to be controlled. Then what we need to control? We need to control velocities. So what kind of velocities? We have linear velocities and we have angular velocities, both of them. So how many of these variables are required to be controlled? So you have 3 forces, 3 moments, 3 velocities linear and 3 velocities angular. So there are actually 12 variables which need to be controlled. And this makes force control very, very difficult. Okay. So now you can appreciate that when the robot was moving around in space, there was no problem. It was moving very easily in space, in free space. The moment there is a constraint coming in, that is interacting with the environment, what is happening is constraints are being put on the task now and on the robot. And by controlling some of these constraints, we have to perform the task. Now, we see that the constraints are of 2 types, natural constraints and artificial constraints. Now, what are these 2? Let us have a look further. In this particular case, now our constraint frame has been put. Okay. Now, in this frame, if you look at in terms of the task, the robot gripper is holding the handle. Now it can apply velocities in particular directions, and it cannot apply velocities in particular directions because of the constraints. What do I mean by that? let's look at the various constraints, the artificial constraints and the natural constraints first. Okay, so the first thing that we'll look at is the natural constraints. So let me rub this out and we will write it here again. So what are the natural constraints? The natural constraints are the constraints on the robot because of the nature of the task or the nature of the contact. Okay, so the nature of contact will enforce some natural constraints. So these are my natural constraints. So let's call this natural constraints. Okay, and let me write them here. On the other side, we have the artificial constraints. Okay, so in terms of the natural constraint, how many constraints are there, or what are we trying to control? There are forces and their moments. So there is Vx, Vy, Vz, omega x, omega y, omega z in terms of velocities. Then you have Fx, Fy, and Fz in terms of forces, and Mx, let's call it Nx, Ny, and Nz in terms of moments. Okay, so there are actually 12 variables. Some of this would come under natural constraints, some of this will come under artificial constraints. Now, in this case of a robot trying to rotate the handle, hold the handle and rotate the crank, what are the natural constraints? So the natural constraints are, if you see, velocity is equal to Vx is equal to 0. Okay, please note this very carefully. Can the robot apply a velocity in the x direction, in this direction? It cannot. Why? Because it is constrained there. So when it is holding the handle tightly, it cannot move the crank in this direction because it is a rigid body there, right? So it cannot apply a velocity in the x direction, which means that the linear velocity, there is a natural constraint on Vx is equal to z. Vx is equal to 0. Can it apply a velocity in the z direction? Again, no. This is my z direction. Can it apply a velocity in that direction, that side or this side? No, again, it cannot apply a velocity in that direction. So my Vz is also equal to 0. So these are constraints because of the nature of the contact or the nature of the task. Okay, and there is nothing the robot can do about it. So now if you want the robot to apply a velocity Vx is equal to, just for example, 10 meters per second, okay, it will not be able. It's not possible because of the constraint. Okay, what are the angular velocity constraints? Now the angular velocity constraints, what about your Vy? Can it apply a velocity in this direction? Yes, it is free to, because it can rotate in this direction, right? So it can apply a velocity in that direction. So there is a velocity which is possible in this direction. Vy is possible. How much it is, we'll just see. Okay, so Vx, Vz are not possible. Vy is possible. Okay, so Vy is in this direction, so we can write Vy dot. So that is possible in this direction, right? Now, what about the angular velocities? Can it hold the handle like this? The gripper is holding the handle, you can see. Can it rotate like this? Can it have an angular velocity about the z-axis, omega x? Is that possible? No, that's not possible. Why? Because you can see the handle is a rigid body there. So you can't rotate it about that axis like that. So again, omega x is equal to 0. And similarly, omega y is equal to 0. Again, it can't rotate like this. It's not possible, right? But it can rotate about the z-axis like this. That is possible. Okay, so omega z comes this side. Okay, so omega z comes this side. Okay, so we have covered which two? We have covered the linear velocities and the angular velocities. Okay, now what do we have to cover? We have to cover the forces. Now let's look at the forces Fx, Fy, Fz. Can it apply a force in the x direction? Now, can it apply a force like this, Fx? Yes, it can apply. Why? Because this is a rigid body, right? So there will be an equal and opposite reaction in that direction from the handle. So it can apply a force in that direction. Okay. So my Fx will go this side. Okay. So Fx is going this side. What about in the z direction again? Yes. So Fz is going that side. Okay. These are artificial constraints. In the natural constraints, can it apply a force in the y direction? In this direction, Fy? No, it can't apply. Why? Because the moment it starts applying, it will start rotating. So Fy is equal to 0 here. That's a natural constraint. Okay. Similarly, Nz, let's look at forces first. So Fy is equal to 0. So fx and fz are artificial constraints and fy equal to 0 is a natural constraint. What about moments? Can it apply a moment about the z-axis? Now the moment it tries to apply a moment about the z-axis, what will happen? It will start rotating. Okay, so it cannot apply a moment about the z-axis. So that becomes an artificial constraint again. Sorry, this becomes a natural constraint. What about moment about the y-axis? Y and the x. Now, can it apply a moment about the x-axis? Which means, can it apply a moment like this? Yes, it can, because there's a rigid body. The handle is a rigid body, so it can, because there is an opposite and equal reaction. So this will come here. So nx is coming here. Okay. Similarly, ny is coming there. These are artificial constraints. Okay. So the only natural constraint in terms of moment is nz, because the moment it tries to apply a moment like this, it will rotate. The handle will rotate, so it can't. There is no opposite and equal reaction. Whereas in the other two cases, x and y, it can do that. So there is these two constraints will become artificial constraints. Now to perform this task, we are seeing that natural constraints are here, okay, and there is nothing you can do about them. They are all equal to 0. That means if you want to have a moment of force in the y direction of having some magnitude, it's not possible, because this is a natural constraint. Whereas on the other side, if you're looking at the artificial constraints, these are constraints which are possible. Okay, so these are constraints which are possible to have motion in those directions or forces in those directions, and hence they have to be controlled. By possible, I mean these have to be controlled to do the task. Okay, now I hope it becomes clear why we have partitioned it like this. This is nothing you can do about it, so there's no question of controlling them. Whereas on the artificial constraints, they have to be controlled. Either you have to make them 0 or you have to give some velocity. Okay. So in order to move this in a particular direction, how are you going to rotate the crank? So you have to apply a velocity in this direction, the y direction, okay, in order to perform the task. And hence you have to say omega z is equal to, let's say, alpha. Okay, omega z is equal to alpha. That is how you're going to rotate the crank. And if you put omega z is equal to alpha, this will become r into alpha. Okay, r into alpha, right? So this is, where is r? R is this one. So this basically means that to perform this task, you need an angular velocity and a linear velocity. Angular velocity about z-axis, linear velocity about y-axis. Okay, and that is how you're going to perform this task to rotate this crank. What about the other fellows? Fx must be equal to 0, Fz must be equal to 0, Nx must be equal to 0, and Ny must be equal to 0. Now this has to be enforced. That means the controller has to ensure that the forces in those directions and moments are 0. Otherwise the task will not be done. So this essentially shows you that force control is actually a difficult task, because you need to control so many variables. Now let's look at another example here. The case of a screwdriver. Now you're familiar with this. You can try taking a screwdriver, insert it into a screw and rotate and see how you are performing the task. Now imagine a robot is going to do this now. Okay, so how will a robot do this? The robot will hold the screwdriver. Okay, so let me say this is a robotic gripper. Okay, so the robot is going to hold the screwdriver, okay, tightly, and then is going to screw the screw to insert the screw into the surface. Okay, now here also the first thing that we do is we put our constraint frame, which is given here by C. So xc, yc, zc is my constraint frame that I put. Now there are constraints because there is contact between the screwdriver, which is held by the robot, and the screw head. Okay, and we have to control what? We have to control Vx, Vy, Vz, omega x, omega y, omega z, and then we have to control Fx, Fy, Fz, and Nx, Ny, Nz. So forces, moments, we have to control. So we partition this into natural constraints. So these are natural constraints, and we have our artificial constraints. Okay, like in the previous case, we simply partition it, and then we see which ones are the ones which are automatically 0. So natural constraints are automatically 0, so there is nothing you can do about them. Artificial constraints have to be controlled. Okay, so first we need to do this. So if you look at this task in the x-axis, y-axis, z-axis, can you move in this direction? No, you can't move in this direction. Why? Because the screwdriver is inserted inside the head, so you cannot move in that direction. Okay, so automatically the natural constraints are going to become Vx is equal to 0. Similarly, we have omega and Vz is equal to 0, because you can't have a velocity in the z direction, right? But y direction is free, so you can actually move in that direction. The head will come off, the screwdriver will come off from the head of the screw, but you can still move in that direction, right? So so Vx, Vy becomes 0. Now omega x is equal to 0 and omega y is equal to 0. So you cannot have an angular velocity in that direction. Similarly, you cannot have an angular velocity in that direction, but you can have an angular velocity about the z-axis. Please note that, right? Now, what are the in terms of Fy is equal to 0 and Nz is equal to 0. Okay. So how do you, if you think a little bit, how do you insert a screw? How do you tighten a screw rather? So you put the screwdriver head, hold the screwdriver, and you rotate in this direction, right? That is how you turn the screwdriver, and you have to apply a small force in this direction also to keep these two, the screw and the screwdriver in contact, right? So that's how you tighten a screw. So what are the artificial constraints? The artificial constraints are Vy is equal to 0, otherwise it will disengage. Omega z is equal to alpha 2, let's say. So we must have an angular velocity about the z-axis, which is our alpha 2, which we are controlling in order to perform the task. Fx must be maintained as 0, Nx must be 0, Ny must be 0, and your Fz must be equal to alpha 3. Okay, so this has to be ensured. Okay, you have to ensure this, otherwise the task will not be done. So how can you do this? We have to control all these variables. So 1, 2, 3, 4, 5, 6 variables have to be controlled here to perform this task, and hence a robot would find it very, very difficult to tighten a screw. If you see industrial robotic applications, very, very often a robot cannot do tasks where there is contact, and that is one problem with robots, because you need to control too many artificial constraints, and some of these artificial constraints are constrained in the sense that the position and forces are orthogonal again. So there is one more constraint actually which is coming. So one way of trying to let's look at the example of peg in the hole assembly. So this is a peg in the hole assembly. So we have a hole and we have a peg here, okay, and I want to insert it. So for example, first what we can do, we can simply put my constraint frame. This is x, y, and z frame. Okay, so what we can say is we can have a velocity in the z direction. Okay, so I have a velocity in the z direction. So we say Vz is equal to alpha until contact is made. Okay, the moment contact is made, then you can press it inside. Okay, so we can have force Fz is equal to alpha 2. So the moment, what I'm saying is that you have the peg, you push it in this direction because there is free motion, and the moment contact is made, you can sense that contact, and then the process stops. Okay, so for example, if you have peg in hole assembly, this is another example. Now let me take a bigger example. Okay, so we have let's say a base plate, and we have a hole in there, okay, and you have to insert it here. Okay, let's look at this example. Okay, what are the various steps of motion? Suppose this peg could be anywhere else. So what we can do is we can move it downwards, okay, and see where contact is being made. So the moment contact is made, you can sense the force. Let's say this is my Fx, y, and z here. Okay, so suppose this is my x, y, and z. I move with a force in this direction. Contact is made. That means I know that there is no hole there. Then what I can do is I can move it in this direction and again try this, trying to push it inside. Okay, so the moment it comes to this hole, now you can move in the z direction. Z direction is possible now. Then what you do is move it in the z direction until contact is made again. So essentially you're playing with the velocities in the z direction and the forces in the z direction, okay, in order to insert this peg in hole assembly. So again, it is going back exactly to what we were talking here, that which forces and which motions are possible in terms of the constraints which are there. You can divide them into natural and artificial and then proceed. Now let's look at something which we call hybrid force position control. Now in hybrid force position control, for example, this is an object, and a robot is holding them. Let's say this is a robot gripper. This is a robot gripper. Okay, let me draw it like this. So this is a robot gripper, and the robot gripper is closing. Okay, so when it is closing, it is in free space, it is in position control. Okay, so first it is closing, the robot gripper is closing, so this is in position control. Okay, so no contact is there. The moment contact is made, for example, this comes and makes contact with that, you have to switch to force control. Okay. So this means that when you are in position control, this finger is closing. Okay, so you are in position control, you are controlling the position. The moment contact is made, you cannot close the finger anymore because you are constrained. So you have to switch to force control and then apply a particular force. So which means that you are either in the position domain or you are in the force domain, but you are not in both of them. Okay, and in between force and position, there is some kind of switching going on, and there are problems associated with that. But this type of control is basically called hybrid control. And in hybrid control, let me draw the block diagram. So this is a position controller. Okay, and this is my force control. So there are two separate controllers, and this is my position input. Okay, so x desired double dot, x desired dot, and xd. This is the position mode. Okay, and then in the force control mode, we have force. So we have force desired, and this is all going on to the constraints, to S, and this is my constraints. Okay, so this is my constraints which are there, and this is coming here, this is going there. Okay, and this is my actual this is my robot arm or robot finger in case of gripper. This is going with feedback here, and this is going with feedback onto the other side. Okay, so this is my feedback which is going. Now if you look at this case and try to correlate with the previous one, this is a robotic gripper which is trying to grasp this object. Now if you look at this example, it's very clear that you are either in the position domain or you're in the force domain. You're not in both, and you cannot control both simultaneously. In the human arm also it is the same, human hands I mean. When you catch an object, you first close your fingers, right? So you're in position control. The moment you make contact with the object, now you can't control your position anymore because you're constrained. So you're in force control now. So this is essentially what is being shown here. So you're either in position control domain or you're in force control domain, and there is switching between the two. Okay, so this is my constraints which are coming. Okay, so either you're in position domain or you're in force domain, but you're not in both of them simultaneously. Okay, so this type of control is basically called hybrid control. So a lot of robots which make contact or are used for grasping, they work on hybrid control, where they're in position domain and then they can switch to force domain. Now let's see further in terms of tasks. So here we were talking about force control, and force control essentially deals with contact tasks. Okay, how do we control such tasks? We talked about natural constraints and artificial constraints. Now let's see how do we actually control them. Okay, this is very interesting because a lot of the problems here have still not been solved. Okay, we understand PD control, PID control very well, but not force control. Okay, so in order to control contact tasks, in order to control force, okay, we normally use PD control, motion control in terms of partially constrained tasks. Okay, this is one way of controlling. Hybrid control I just explained. Then there is something called impedance control. Okay, so position control mode is basically PD PID control, which is used for position control only, or motion control in free space. Whereas force control is essentially for partially constrained tasks. We have hybrid control where you are controlling force or motion, and you have another type which is called impedance control, where you have a relation between the force and the position, and you actually go in the position domain by finding this relation between force and position. This is something I'll talk about now. So before that, let's talk about PD and PID control of force. Okay, so the examples that we are looking at, what are the various examples? These two are examples. Let me explain this so it becomes easier. So this is a robot in a grinding task. The robot is grinding. There is a grinding wheel you can see there, and this is my grinding wheel there. Okay, so it is making contact with the object and applying a force, and it is moving in a direction which is orthogonal to it. So this is an application of constraint task. The picture on the right is a robot writing on a surface. So this robot here has a pen. You can see the pen, the black color marker pen, and it has to draw this line on the surface. Okay, like that. So it is writing on a surface now. Again, it is constrained. Why? Because for writing, it has to apply a force in this direction and it has to move in that direction. Okay. How do we design such kind of controllers using PD controllers? That's something we are looking at here. So what we are doing here is that we are writing our equation in this form. So our equation for the robot is equal to, the dynamic equation is mass into acceleration plus Coriolis and centripetal force plus gravity forces plus tau external, which is the external force that is being applied. So this is the applied force the robot is applying onto the environment. This is my dynamic equation. Now to control this torque, I can put a controller like this, where tau is equal to k, this is kp into the position, and this is kd into the velocities. Okay, so this is my desired position, this is my desired velocity. Okay, so this is basically my error. And I'm writing my the dynamic components, mass into acceleration, Coriolis, centripetal plus gravity here. Okay, now mc, g, and h are the internal model of the corresponding mechanical terms of the robot. So if I take this tau and put it here, okay, then what will happen is I'm going to get. So if you look here a little bit, okay, what is going to happen is we are going to get this term. Okay, so we have my kp into this term and kd into that term plus m. This is my inertia matrix into this is my desired acceleration minus the acceleration is equal to tau external. Okay, so again, so this is the controller I'm proposing. Okay, so what I do is I put it in here, and what we do get is the Coriolis centrifugal terms. Some of them are going to cancel. This is going to cancel off. What will be left with is this term, the inertia term. Okay, and this is my equation which I'm going to get. Now this is basically a PD controller equation. Okay, so which means that I'm controlling my external applied force by using a position controller, which is simply controlling the errors in the position, velocity, and the accelerations. Okay, now if I say qd minus q is equal to E, okay, then what we get is this equation now. Okay, so this is one way of controlling the external force that the robot is going to apply. Okay, and we can play with these gains, the position gain and the derivative gain. In the beginning of today's lecture, I talked about the stiffness. Okay, now this k and d are basically have dimensions of stiffness and damping. Okay, so by changing the stiffness and the damping, you can make this arm behave in a particular way. So when I talked about when I showed you the video of the robot arm, where the human being was pushing the robot arm and the robot arm was behaving in a particular way. Now this behaving is being enforced by changing the k and the d matrices, okay, which are basically the stiffness and the damping matrices. So this is one way of controlling the stiffness and the damping of the robot arm